simple example. Let us say I am taking a shaft. Okay, I am having a shaft, right? This shaft is sitting on two bearings. Like this is my bearing, one bearing and two bearings. Okay, so there is a shaft with two bearings, and the shaft has a central mass attached to it through a distance. Let us say this is the linking element, and this spherical component is my mass. Okay, this sphere is the mass. We assume that this link has no mass. Okay, there is a negligible mass. Maybe I have drawn it a big diameter. Maybe the diameter is very small. Okay, uh, this linking element mass is very negligible. Now I am having a particular amount of mass attached to a shaft which is rotating about the axis, this axis. Okay, which is rotating about this axis, and this mass is about to go around your shaft and start to create a disturbance in the equilibrium of the shaft, right? We are having a shaft like this. Now I am going to fix a motor here. Okay, and then switch on the motor. What will happen? Naturally this mass will tend to pull the shaft outwards wherever it is going because of centrifugal force, correct? Now I want to balance this mass. Okay, I want to create some sort of an arrangement which makes sure that the shaft will not be disturbed from equilibrium. Now this is what we are going to do in this unit. So there are two types of balancing. Okay, so within the rotating masses itself, one first type of balancing is called static balancing, the second type is called dynamic balancing. Okay, so what is static balancing? So if you you create, let us take this same example what you have seen earlier. If I put an exactly same amount of mass at the particular at the same amount of radius 180-degree away from this mass, let us say I am going to do something like this. So now what will happen? Just imagine. Now if I switch on the motor, whatever amount of disturbing force this mass is going to create, a same amount of disturbing force will be created by this mass in the opposite direction. So therefore those two vectors will cancel each other. Do you get it? Right? Uh, I think my screen is visible to you. Can you see my screen? Someone tell me. Okay, fine. So please understand my question. Earlier it was like this. Okay, there was only one mass which was disturbing me when I started rotating. Uh, don't worry how this can be, where this will come, what is the application. That and all you don't worry now. My simple question: there is a shaft like this. There is a motor attached. Let us say this is my motor. Shaft is going to rotate. Now this mass is going to pull your shaft out due to the centrifugal force. Now the solution is to add another mass opposite to it. Now what will happen? The disturbing and another disturbing force which is exactly equal in opposite, equal in magnitude but opposite in direction to your previous force will have start and exactly balance out the disturbing force. Now this is one way to balance. Okay, so now that's a very simple case study, right? So now let us take this example. What is the difference between static balancing and dynamic balancing? Okay, so now it happens in case if you have the masses concentrated on only one side of the shaft. Okay, if you the masses are located on only one plane, correct? Can you see the plane? The plane is in green color. The mass, all the masses that I have added, let us say three masses were there earlier. I found out the resultant and I have added the fourth mass to balance out. Now it is exactly dynamically balanced. No disturbance occurs in the bearings. Now, when all the masses in the consideration, under consideration, all the masses under consideration, under discussion, under calculation lie in a single plane, or all the center lines of the masses lie in a single plane in this as in this diagram, then the balancing that you have done is called as a static balancing. Very simple. Okay, if all the masses are lie in a single plane, disturbance occurs only in the middle of the shaft or one third of the shaft or only one place, and you put the balancing mass also in the same plane, then it is your static balancing. Okay, let us look at this. If you have masses in multiple planes, different places, okay, far away from each other, then this system requires a dynamic balancing. That is the major difference between static and dynamic balancing. Okay, so in the problems wherever you go, the given data, some problems may have your this data, what is the inclination between each mass, that will be given to you. But looking from this side, you have no clue whether it is a static or dynamic system. So for that, you have to have a look at this. What is the distance between each mass? Clear? So when you look at from one side view, you can never tell whether it is a static system or a dynamic system, right? Everything appears the same. Same here. You come here. Now this is a static system, right? Everything is in the same plane. Now I am going to put it in the side view. Now can you differentiate this and this? Have a look at this. Now have a look at this. No difference. Correct? But when you take a left view, you can see the masses are far away. It is in one, this is in one plane, this is in another plane. There is a small distance between these two, and there is further distance between these two, and further distance between these two, right? It keeps, so this system requires a dynamic balancing, whereas this requires a static balancing. Okay, clear? So that is the main difference I wanted to convey. So what we do here in this case, what we do, we go for creating force polygons and couple polygons, and then we finally end up with the resultant force. We find out where is the resultant force located, and we put an opposing mass. We create a opposing force to that resultant, so that the resultant force is cancelled out. So that is the basic idea between balancing. Now what I have been talking about is entirely rotating masses only, not reciprocating. Okay, first we will see only rotating masses. Clear? So rotating masses, two methods of solving: static balancing, dynamic balancing. Static balancing means everything lies in the same plane. Even your balancing mass also comes in the same plane. Dynamic balancing, they lay across the length of the shaft, multiple angular positions. This need not be exactly 90 degrees to each other. Just I have given you an example. Okay, it may be at any given inclination. Now in any given diagram, if you look in the book, you will have this data. What is the angle of inclination between each, and then this data will be given. What is the distance of planes between each masses? What is the distance between this plane and this plane? This axis line. Okay, this distance and this distance. These distances between the masses will be given, and the angle of inclination between the masses will be given. But you have to think about it and find out the resultant. So that is the basic idea of what are all the problems involved. Clear? So static and dynamic, I think you are clear now. Let's move on. I think I can close the Creo. So that is the basic idea. Let's go through some slides. So the high speed of engines and other machines is a common phenomenon. So we keep on increasing the speed of our machinery. It is not going down. It keeps on increasing. Very essential that all rotating and reciprocating parts should be balanced. For an example, take a fan. If your fan is unbalanced, what will happen? It will keep shaking, and one day it might create a fatigue failure of the shaft which is carrying your fan, and it will fall on the head of people. So it should be perfectly balanced. It should not create any oscillation, or the oscillation or the vibration should be as minimum as possible. If these parts are not properly balanced, dynamic forces or vibrations set up inside the parts. These forces not only increase the load, so there are a lot of stories to some things we have to go through, but I don't have really time to talk about it since our exams are very close. This PPT will be shared to you. Please have a go through that. Okay. So the types of balance, these are theoretical. We don't actually do all these things. We do only two types of problems. Static, all the masses lie on the same plane. Okay, balancing mass also lie on the same plane as I shown you in the Creo. Second case is your dynamic balancing. The masses lie at different angular position across the length of the shaft. So those are the only two types of problems. These things you can study for 2 marks. Okay. So balancing of a single rotating mass by single mass rotating in the same plane. This is how to derive the formula, all that. So because of shortage of time, I cannot do this. Okay, so the basic idea is you have to understand m omega square r is a formula for centrifugal force. If you put a mass at some radial distance from the axis of the shaft, some mass m1 at a distance r1 away from the axis of the shaft, and then you start rotating the shaft, what is the centrifugal pull created by the mass? C equal to m omega square r. M is the mass of that particular mass you have attached. R is the distance from the axis of rotation, radius of rotation. Omega is the speed of rotation. M omega square r is the centrifugal force formula. Okay. So when you want to balance a force, you have to find the summation of vector sum of all the masses. I mean here in a static balancing case. Okay. Vector sum of all the m omega square r involved, and then find the resultant magnitude and direction, and you have to oppose that with your balancing mass. So that is the idea. Okay. Centrifugal force is the most important thing here. Right. So static balancing, same plane. So this side view is what I have shown you in the cryo. Now this side view does not tell you whether it is a static problem or dynamic problem. Okay. Just looking from the side, you cannot tell whether it is static or dynamic. The magnitude and position of the balancing mass may be found out. There are two ways of doing problems: analytical method and graphical method. We will be concentrating only on graphical method. Okay. So analytical method involves a lot of calculation. It is unnecessary. So now have a just look at this diagram. What we are going to do in analytical method, what we do. So each arrow mark represents the resultant force created by each mass. So let us say some 5 masses are attached in this case. So FC2, FC1, FC2, FC3, FC4, and 4 masses are attached. These are the resultants. Now I am going to find out the horizontal and vertical component for each force. So FC3, so this FC3, look here, this FC3 force is represented, resultant force is here, it has 2 components, horizontal and vertical. Similarly, FC1 horizontal, FC1 vertical. Similarly, all the forces are resolved as horizontal and vertical. Horizontal are summed up and vertical are summed up, and that is how you find out the analytical solution. So sum of the horizontal components, sigma h is equal to m1 r1 cos theta, m2 r2 cos theta 2, m3 r3 cos theta 3. See, I believe you are understanding. Okay. So this force is because of m1 omega square. So omega is same for everything, right? They are all sitting on the same shaft. Therefore, omega will get eliminated. M into R. Okay. So that's what is written here. And if this is my resultant, what is the horizontal component of that? Cos theta. So that's what is written here. M1 R1 cos theta, M2 R2 cos theta. How you eliminated all the omega? Because all the masses are going to go around at the same speed. So you can directly eliminate omega divided by omega. Okay. So because all the masses are on the same shaft, it is going around in the same speed. Omega gets eliminated. M1 R1 cos theta, M2 R2. So this is my horizontal component. Vertical component, sin theta. Okay. So now I am going to, like your Pythagoras theorem, summation of your horizontal and vertical forces, sigma h square plus v square, will give you the magnitude of the resultant force. Okay. Magnitude of the resultant unbalanced force. Direction, sigma horizontal by sigma vertical. So don't worry about this. Just have a look at this. When you are doing the problem, it will become very clear to you. So one important thing you have to understand. Let us go back to this diagram. I will tell you. So let us say what I have written here. Please see very carefully. Listen. I am with all the calculations. I am finding out that the resultant force is like acting like this with so much of Newton magnitude at a particular value of theta direction. Okay. So I have found out the answer. Now how do you balance out this? You take an exactly same amount of m omega square r and put it diametrically opposite, so that I generate an equal and opposite force, so that they get cancelled, and the forces, there are no unbalanced forces left in the system. Therefore, whatever answer you are going to find out for theta, so let us say the resultant force direction I am finding out as theta of resultant plus 180 will give you the direction of balancing mass. It should be diametrically opposite. You have to find the resultant force and put a mass in a direction opposite to that. Okay, so that is a basic area. That's very important. So all these are some fundamental formulas. Graphical method. I don't think discussion of graphical method is required here. Directly we will do a problem.